I always know when it actually don't know when it actually starts recording. I get this little wheel of death. Anyway, just to explain some weird staring that might have gone on. For our last little lecture on atomic structure, we're going to look at radioactivity. And so nuclei, especially as they start to get larger and larger, will become unstable. And unstable nuclei will emit radiation until they do become stable. Radiation will typically take the form of either high energy electromagnetic radiation, think things like X-rays and gamma rays, or very high energy particles. One of those particles that might be emitted is called an alpha particle. And so some radioisotopes are alpha particles. Alpha particle is a very slow moving, very high energy particle that consists of 2 protons and 2 neutrons. It's essentially a helium nucleus in that way. And so it has a charge of +2. This means that when an alpha particle is emitted from a nucleus, the resulting what we call daughter nuclide, which is the nucleus that's left over after the alpha particle leaves, that resulting daughter nuclide has a mass number that goes down by 4 and an atomic number that goes down by 2. Now think about what that means for just a minute. If the atomic number changes, what does that mean for the element? It changes its identity. And so this type of radiation, this type of radiation that a nuclei undergoes will actually change the identity of the element. Let's look at an example. So here we have 226 radium. And so a mass number of 226, atomic number of 88, which makes it radium. When it goes through alpha decay, our mass number, we can see, goes down by 4, and our atomic number decreases by 2. And we look on the periodic table to see that 86, where's 86? Where are you? Okay, it was behind me over here. Right here. And so we see that when it goes from 88 to 86, we look it up on the periodic table and we see that that is now radon. And so we've gone from having 226 radium to now having 222 radon, plus our alpha particle is also emitted. And here's just what we would call the radiation equation for that. And so in this example here, this is plutonium-239. We can see again our mass number goes down by 4, our atomic number goes down by 2 to form uranium-92. And uranium-235, atomic number 92, and our alpha particle. This doesn't happen quickly. This process here for plutonium can take up to 24,000 years. It's one of the reasons why radioactive waste is so dangerous. It stays around for a long time until it starts to become a little bit more stable by spitting out some of these radioactive particles. Another fairly common type of radioactivity is called beta emission. A beta particle is almost like a very high energy electron. What happens when beta emission occurs is that a neutron is actually converted over to a proton as well, for some reasons that go well beyond what we're going to talk about in this class. But just know that that is the net effect. And so that means that the mass number will stay the same, right? A neutron to a proton. Remember, the mass number is the sum of neutrons and protons. So if we're just converting one to the other, the mass number stays the same, but now we have one more proton. So the atomic number increases by 1 with beta emission. So here's an example of that. So here we have 218 polymonium. So again, our mass number stays the same, but now our atomic number goes from 84 to 85. And so our new element is astatine. And then our beta particle is emitted. And we can see that as well down here. Here's hydrogen 3, which is called tritium. Hydrogen-3 will decay by beta emission to form helium-3. So again, our mass number stays the same, but our atomic number goes up by 1. And that's the hallmark of beta decay. This time that it takes for it to occur, if you've maybe heard of half-life. So half-life is the amount of time, if you have a certain sample of a certain number of these nuclei, half-life is how long it'll take for half of these to decay through that process. And so when we're looking at these numbers here, this 12.3 years, for instance, that's our half-life. And so if I had 100, just throw a number out there, if I had 100 tritium particles, in 12.3 years, 50 of them would now have decayed into helium-3. The other 50 are still tritium, and now it's going to take another 12 and a half years for 25 of those to become helium-3, and so forth. Half-life, depending on the compound, can vary anywhere from fractions of a second to billions of years. Just depends on the particle and then the type of radioactivity. Radioisotopes are quite often used for various medical applications. And so it should be pretty obvious and pretty intuitive that for those types of applications, we really want short half-lives in order to minimize a patient's exposure to any radiation. And this is a good demonstration here or a good visual of the various penetrating power of X-rays, or sorry, of radioisotopes in general. Alpha particles, they're pretty big, pretty bulky. Alpha particles you can literally stop with a sheet of paper. Beta particles, a little bit more energy. They'll blast through a sheet of paper pretty easily, but they'd be stopped by aluminum, which is a pretty thin metal. X-rays, now we're getting even more energy. X-rays are going to penetrate paper, X-rays are going to penetrate aluminum, but they would be stopped with some thin lead. That's why, for instance, if you're in the dentist's office and you're getting some X-rays on your teeth, they're going to drape you with a lead apron, and that's going to make sure that any of the X-rays that are coming out are really only going to where they need, and they're not entering any of the rest of your body. Gamma rays, on the other hand, now you need some really thick lead. You need a really thick lead plate to stop those. Actually, not going to bother talking. Well, yeah, that's just about the units of radiation. We're not going to really worry about that too much for this course. Radiation exposure could be either acute or chronic, and so it might be something that's just sort of a little bit harmful, but not real bad for you. That you might get a little bit of radiation sickness from. The severity of symptoms would be directly proportional to the dose that you had. The benefits of controlled exposure can often outweigh the risks. And so think of, for instance, well, like X-rays for when you're getting your teeth X-rayed. Think of cancer treatments. Cancer treatments are quite often used, or quite often radiation is involved with cancer treatments, because the benefit of that controlled exposure of killing off and destroying the cancer cells outweighs the risk of damage to other parts of your body. And I was just looking to see if I don't really need to talk about any of the rest of this. And so that concludes our lesson on radioisotopes, and that finishes up our look at atomic structure in general. And so I said that I was looking for a new sign-off, and I think I am going to take I'm going to go ahead and steal liberally from Ron Burgundy and say, you stay classy, USM. Good night.